Dear students, welcome back to the lecture series on solid state. In this session, we will have a discussion on the laws of crystallography. There are three fundamental laws of crystallography. However, in this session, we will be discussing the first two laws, namely the law of constancy of interfacial angles and the law of symmetry. Before moving on to today's topic, let's have a discussion on the answers for the assignment questions of the previous class. The first question was, what is meant by crystallization? You are given four options. Option A, concentration of atoms into highly structured form. Option B, solidification of atoms into a highly structured form. Option C, solidification of solution, and option D, concentration of solution. We have seen that crystallization is a process in which atoms will arrange themselves in a well-ordered manner and precipitate out. So, the correct answer is option B, that is solidification of atoms into a highly structured form or a well-organized form. Now, we will move on to the second question. Why is a supersaturated solution unstable? The options are: concentration is higher than the equilibrium concentration. Option B, concentration is lower than the equilibrium concentration. Option C, concentration is equal to the equilibrium concentration. And option D, contains impurities. And we have seen that while discussing about supersaturated solutions. What is a supersaturated solution? A solution which contains more solute. So, the concentration of solute is more in a supersaturated solution. And because of the large concentration of solute, a supersaturated solution becomes unstable. So, the correct answer is option A, that is the concentration is higher than the equilibrium concentration. So, when the concentration of solute is higher than the equilibrium concentration, the solution becomes unstable, and that paves the way for crystallization to begin. Question number 3. The nature of the crystallization process is governed by option A, thermodynamics, option B, kinetic factors, option C, thermodynamics and kinetic factors, and option D, none of the above. We have already discussed about the crystallization process. Various factors affect the crystallization process. The nature of the crystallization process is governed by both thermodynamic and kinetic factors. So, the correct answer is option C, thermodynamic and kinetic factors. Now, we will move on to the next question. What is nucleation in crystallization? Option A, it is the initial step in crystallization. Option B, it is the final step in crystallization. Option C, it is the step where nucleus is added. And option D, it is the subcategory of crystallization. We have seen that crystallization process proceeds via two stages. The first stage is nucleation, followed by the second stage, which is crystal growth. And nucleation is nothing but tiny ordered arrangement of atoms to form a nuclei. So, among these options, the correct answer is option A, it is the initial step in crystallization. Nucleation is nothing but the birth of crystals, and it is the first step in crystallization. The last question, what is homogeneous nucleation? Option A, spontaneously generated nuclei. Option B, randomly generated nuclei. Option C, orderly generated nuclei. And option D, randomly and spontaneously generated nuclei. We have seen that nucleation is of two types, homogeneous nucleation and heterogeneous nucleation. In homogeneous nucleation, there will be randomly and spontaneously generated nuclei, tiny ordered arrangement of atoms to form nuclei, and these atoms will be randomly and spontaneously generated. Therefore, the correct option is option D, randomly and spontaneously generated nuclei. Now, we will move on to today's topic, that is the laws of crystallography. So, before discussing the laws of crystallography, let's get familiarized with the term crystallography. We have seen that a crystalline solid is the one which has a regular, well-ordered, repeating geometrical pattern throughout the entire three-dimensional structure. So, a crystal is a solid entity in which its structural units are arranged in a well-ordered, regularly repeating geometrical pattern. So, what will be crystallography? It is nothing but the study of crystals, or we may say the branch of science which deals with the geometry, properties and structure of crystals is called crystallography. So, crystallography is the branch of science which deals with the geometry of the crystals. It deals with the properties, various properties exhibited by the crystalline solids, and also about the structure of crystals. Now, let us see some common terms used in crystallography. The first one is crystal habit. Crystal habit refers to the external shape of a crystal. There are many factors that affect the external shape. The way a crystal grows include factors like temperature, pressure, and also the presence of impurities. So, external factors like temperature, pressure, or the presence of impurities can significantly impact the crystal habit or can significantly impact the external shape of a crystal. So, on the screen you can see a variety of crystals exhibiting various shapes or crystal habit. For example, one type of crystal habit is acicular, which has a needle-like appearance. So, you can see here acicular crystals or needle-like appearing crystals. Another one is bladed or having a flat knife-like appearance. So, this is an example for a bladed crystal habit. Now, next is equant. That means approximately equal dimensions in all directions. So, you can see here an equant crystal having equal dimensions in all directions. So, next type of crystal habit is fibrous, having an elongated thread-like appearance. So, on the screen you can see here green thread-like fibrous crystals. So, next type is prismatic, having an abundance of prism faces, then followed by tabular, having a plate-like or a sheet-like appearance, tabular crystals. So, these are some common crystal habits exhibited by various crystalline solids. So, crystal habit refers to the external shape of a crystal. Various factors such as temperature, pressure, presence of impurities, etc. influence the external shape or the crystal habit of a crystal. These are some other terms in connection with crystallography. The first is the face of a crystal. It is nothing but the bounding surfaces of a crystal which are generally flat. The flat surface of the crystal is commonly referred to as face. The second one is form. Faces in a crystal may be like or unlike. So, each set of similar faces of a crystal is called a form. The next one is the edge of a crystal. The line along the intersection of the two adjacent faces of a crystal is referred to as the edge of the crystal. And the last one is the interfacial angle. Interfacial angle refers to the angle between adjacent faces of a crystal. So, we have a face which is the flat bounding surface, a form, each set of similar faces contributing to a form, and edge, the line along the intersection of the two adjacent faces of a crystal, and the interfacial angle, which is the angle between the adjacent faces of a crystal. So, here you can see a cubic crystal. So, this flat surface of the crystal is called the face, and the line along the intersection of the two faces is called the edge, and the angle between the two adjacent faces is called the interfacial angle. And this interfacial angle can be measured by an instrument called goniometer. Interfacial angle is the angle between two adjacent faces which can be measured using goniometer. Given below represents the forms of a crystal. We have seen that each set of similar faces contribute to a form. So, in figure A there is only one form, that is one set of similar faces. In figure B also there is only one set of similar faces, whereas in figure C you can see two sets of similar faces. So, this one contribute, this is similar to this one, these two are similar, so this contribute to one form, and here on the top and the bottom represents another set of similar faces. So, in total there are two forms in figure C. So, these are some common terms used in crystallography. Now, let us move on to the laws of crystallography. There are three fundamental laws of crystallography, namely the law of constancy of interfacial angles, the law of symmetry, and the law of rationality of indices. And in this session, we will be discussing the first two laws, namely the law of constancy of interfacial angles and the law of symmetry. What is the law of constancy of interfacial angles? We have already discussed about the interfacial angle. It is the angle between the two adjacent faces of a crystal. So, according to this law, the angle between the corresponding crystal faces remains the same for a given substance, no matter how the faces develop. This is also known as Steno's law, and this is the first law of crystallography. So, the first and fundamental law of crystallography is the law of constancy of interfacial angles, also known as Steno's law, which states that the angle between the corresponding crystal faces remains the same for a given substance, no matter how the faces develop. This law was discovered in 1669 by the Danish geologist Nicolas Steno. He observed that although quartz crystals differ in appearance from one to another, the angles between the corresponding faces are always the same. And it was this observation that led him to state the law of constancy of interfacial angles. So, on the screen you can see a cross section along prism and rhombohedral faces indicating the constancy of interfacial angles. So, in this figure you can see that even if the quartz crystals are flattened along one axis, the angle will still remain the same, that is about 120 degree. So, this is known as the law of constancy of interfacial angles. The second law of crystallography is the law of symmetry. Before moving on to the law of symmetry, let us familiarize with the term symmetry. Symmetry is not just a scientific concept, but a fundamental organizing principle of our world. Symmetry can be seen in nature and all around us. For example, a human body can be divided into exactly two halves. Similarly, a butterfly. So, we may say that these two possess a bilateral symmetry, because one half of it is exactly the mirror image of the other half, and this is called a bilateral symmetry. For example, in this flower, we can see a radial symmetry, all the lines passing through one common center, so radial symmetry. Another example for symmetry can be seen in this snowflakes. A beautiful hexagonal symmetry can be seen in snowflakes. So, nature favors symmetry because it often represents efficiency, stability and optimal use of resources. The symmetry we observe in the macroscopic world is often a reflection of symmetry at the atomic level. For instance, the hexagonal shape of a snowflake is directly related to the hexagonal arrangement of water molecules in ice crystals. So, from a crystallographic point of view, we can define symmetry as the property where a crystal structure remains unchanged. A crystal structure remains unchanged means it will give identical appearance after certain geometric operations. So, from the context of crystallography, we can define symmetry as the property wherein a crystal structure remains unchanged or it gives identical appearance after certain geometric operations. Now, what are these geometric operations? And these operations include rotations, reflections, inversions and translations. Okay. So, whenever we perform such a geometric operation, if we perform a rotation or reflection or inversion or a translation, If you are getting an identical appearance, then we may say that that crystal possesses a particular symmetry. Why symmetry matters? Understanding symmetry in crystals is crucial because it determines the physical properties like optical property, mechanical property like mechanical strength, conductivity, electrical or thermal conductivity, etc. It also allows us to predict and understand X-ray diffraction patterns. We will be discussing in detail about X-ray diffraction patterns in the later classes. Now, the third point is it provides a framework for classifying the millions of known crystal structures. And finally, symmetry guides the design of new materials with specific properties. So, before moving on to the law of symmetry, let's see what are symmetry elements or element of symmetry. A symmetry element or element of symmetry is a geometrical entity such as a line, a plane or a point with respect to which a symmetry operation may be performed. Okay. So, symmetry element or element of symmetry is a geometrical entity such as a line, a plane or a point with respect to which a symmetry operation may be performed. Generally, there are three elements of symmetry with respect to crystals. The first one is axis of symmetry, plane of symmetry and center of symmetry. Now, we will discuss it one by one. First one is axis of symmetry. The axis of symmetry or otherwise known as proper rotation axis is an imaginary line around which a crystal can be rotated by a specific angle to produce an identical appearance. So, it is an imaginary line around which this crystal can be rotated, and when that operation is performed through a specific angle, the crystal will give an identical appearance. Then we can say that that particular crystal possesses an axis of symmetry or proper rotation axis. Since we are performing a rotation, the symmetry operation here is proper rotation. And generally, this is represented as Cn, capital C with a subscript n, or we can say it is an n-fold rotation axis where n is the order of rotation. So, generally represented as Cn where n represents the order of rotation. A rotation of the crystal about the axis through an angle of 360 by n degrees produces an equivalent configuration. We know that when a crystal is rotated through 360 degree, definitely it will give an identical appearance. So, rotation through 360 degree is referred as a C1 axis, and definitely all elements when rotated through 360 degree will give an identical appearance, and hence it can be treated as a trivial element. Now, what happens when a crystal is rotated through 180 degree? A rotation through 180 degree is referred to as a C2 axis. That is, if a crystal when rotated through 180 degree gives an identical appearance, we can say that that crystal possesses a C2 axis of rotation, or it is also known as a diode. For example, in water molecule, that is H2O, when rotated through 180 degree, it will give an identical appearance which is indistinguishable from the original position. So, we can say that a water molecule possesses a C2 axis of symmetry. Similarly, we can call a threefold axis, or that is a C3 axis or a triad that requires a rotation of 120 degree. A fourfold axis, also called tetrad, or we may represent it as C4. So, that requires a 90 degree rotation. A sixfold axis, also called hexad, requires a 60 degree rotation, or we may represent it as C6. Now, why only certain rotation axes? We have seen that only these specific rotation axes, that is C1, C2, C3, C4 and C6 can exist in crystals. This is due to the constraints of space filling in 3 dimensions. For example, a 5-fold or a 7-fold symmetry cannot repeat periodically to fill space, making them impossible in true crystals. And this unable to repeat periodically to fill space is referred to as the crystallographic restriction theorem. So, due to the constraints of the space filling in 3 dimensions, only the above said rotation axis, namely C1, C2, C3, C4 and C6 is normally possible in true crystals, while a 5-fold or 7-fold rotation axis of symmetry is generally not observed in true crystals. So, next element of symmetry is the plane of symmetry. It is an imaginary plane across which a crystal structure is reflected to produce an identical configuration, and this is referred to as the plane of symmetry or mirror plane. Since a crystal structure is reflected to produce an identical configuration, the symmetry operation is reflection. That means, when we look at a crystal structure with mirror symmetry or plane of symmetry, one half of it will appear as the mirror image of the other half. Then we can say that that crystal possesses a plane of symmetry or mirror plane. Given here are the 9 planes possible with regard to the symmetry of a cube. On the top, we can see a plane parallel to 2 opposite faces. So, there are 3 such planes, and these are called the rectangular planes of symmetry. Rectangular planes of symmetry. So, total 3 rectangular planes of symmetry. And the rest, you can see that these are the diagonal planes passing through the crystal in a diagonal manner. So, all these are diagonal planes of symmetry. So, there are a total of 6. So, these are called diagonal planes of symmetry. There are total of 6 diagonal planes of symmetry. So, in total there are 9 mirror planes or plane of symmetry for a cubic crystal. And the next element of symmetry is the center of symmetry. It is an imaginary point through which any straight line passing through it connects identical features on opposite sides at equal distances. This is called the center of symmetry, or it is also known as inversion center. That is, if we draw a line from any atom through this center point and extend it to an equal distance on the other side, then we can find an identical atom. If it is so, then we can say that that crystal possesses an inversion center or a center of symmetry. For example, in this cubic crystal, suppose there is a point at the center of the cube and there may be atoms at all the corners. And suppose we draw a line from this atom passing through the center and extend it to the other side of the atom. So, if the line touches the both atom at equidistant from the center, then we say that the crystal possesses a center of symmetry or inversion center. And crystals with a center of symmetry are called centrosymmetric crystals. A cubic crystal is a very good example for a crystal with a center of symmetry. Some crystals may not have a center of symmetry because they develop differently at opposite sides. So, we have seen the various symmetry elements possessed by a crystal. We have the axis of symmetry or proper rotation axis, plane of symmetry and the center of symmetry. Now, let us see what is meant by the law of symmetry. According to the law of symmetry, all crystals of the same substance possess the same elements of symmetry. Okay. All the crystals of the same substance will contain the same elements of symmetry. That is, it will have an axis of symmetry, a plane of symmetry and maybe the center of symmetry. For example, a cubic crystal will have a total of 23 elements of symmetry. It will have one center of inversion at the center of the cube, a 4-fold rotation, that is a 3C4 axis passing through the centers of opposite faces, 4 3-fold rotation axis or 4C3 axis passing through opposite corners, 6 2-fold rotation axis, that is 6C2 axis passing through the midpoints of opposite edges, 3 rectangular planes of symmetry and 6 diagonal planes of symmetry. So, in total it will have 23 elements of symmetry. Sodium chloride or NaCl belongs to a cubic lattice, and according to the law of symmetry, all the crystals of NaCl will have these 23 elements of symmetry, that is the same elements of symmetry. So, these symmetry elements contribute to the 48 symmetry operations that can be performed on a cube, making it one of the shapes with the highest possible symmetry in 3-dimensional space. So, in today's topic, we had a discussion on the laws of crystallography, and among the 3 laws, we discussed the first 2 laws. So, before discussing the laws, we got familiarized with the term crystallography, some common terms used in crystallography including crystal habit, phase, form, edge and interfacial angle, followed by the discussion on the first 2 laws of crystallography, namely the law of constancy of interfacial angles and the law of symmetry. And in order to understand the law of symmetry better, we had a detailed discussion on various elements of symmetry, namely axis of symmetry or proper rotation axis, plane of symmetry and center of symmetry. Now we will have some discussion on assignment questions. First question, according to the laws of crystallography, what remains constant for the crystals of a substance? Option A, the number of phases. Option B, the size of the phases. And option C, the angle at which the two adjacent phases intersect. Question number 2. Which of the following symmetry element is denoted by Cn? Option A, mirror planes. Option B, a group of proper rotational symmetry. Option C, an inversion center. And option D, identity. Question number 3. The elements of symmetry in a crystal are plane of symmetry, axis of symmetry, center of symmetry, all of the above. Question number 4. List the elements of symmetry for a perfect cube. And the last question, why a 5-fold or 7-fold rotation axis is not possible in true crystals. Please try to find out the answers. We will discuss the answers in the next session. We will continue our discussion on the laws of crystallography in the next class. Thank you.